mesh analysis. Do you guys expect any big surprises here on this one? Don't get your hopes up. Right. Again, we'll see that this works exactly like we would expect, right? So very quickly, we can go through this and put this into phasor form. And in this case, we're asked to find I0, which is just one of the currents here. So here's a good example, right? They ask us to find I0. This is actually a capital I0. But when I look at the circuit, look, it's already in phasor form for me, right? So that means I can give my answer in phasor form, right? And in fact, the one part of this that might seem a little strange is then you say, well, what is omega though? Can you say what omega is? No, you can't. So we really don't know. And it could be anything. You can literally pick an omega. When you pick an omega, though, what it's going to do is it's going to change what this value of capacitance or this value of inductance is. All right? So if you don't know, right here on the circuit schematic, it doesn't say, oh, what value of capacitor is that? I don't know. I could not walk into the lab and build this circuit because I wouldn't know what capacitor to take out of the drawer and put into my breadboard, right? Same thing with multisim. What if you wanted to use multisim to help you solve a problem like this, right? I don't know. So pick one, and it will work. So pick an omega, any omega that you want. Pick something reasonable. Multisim sometimes will outthink you if you tried to go to like really high frequencies, right? Or if you try to get really low, sometimes you'll see some little errors come in because it's not good at distinguishing between, 0.0001 hertz and DC. But if you pick omega equals 1, the math is pretty easy. That's a little slow, but it'll probably work out just fine for multisim at that point, right? So, and math is easy. If omega's 1, great, right? Omega's 1, that's easy. So you can put it in here. However, if you were to build this circuit in the lab, again, an omega of 1 could be a little bit challenging to generate on your equipment. You might not be super happy with the results. So you might want to pick, something like 60 hertz that you feel, this would be what it would look like if it was doing power, right? 60 hertz is pretty reasonable. Again, just convert from 60 hertz into omega, right? Omega is 2 pi f, so you got to multiply 60 by 2 pi. But whatever it is, pick an omega, and then you can go from there. So I don't want you to feel like, I can't simulate this, or I can't build this in the lab because I don't know what frequency, so I don't know what real value of capacitor or inductor I have. It's okay. Now, if you build this for 60 hertz, you're going to choose a capacitor and choose an inductor that yield that value of capacitance, right? You're going to plug in and you're going to say, oh, if omega equals, right, so the capacitor is negative J2, and that I relate to, negative J over omega C. If I plug in 60 hertz or, whatever the equivalent of it, but let's say if I let omega equals 1 even, right? If I plug that in, omega is 1, and I can solve for J, solve for C, right? C is going to be a half. Can I now use that circuit and go to omega equals 100? Will the circuit still be valid? No, it won't. It will have a different behavior. So you can pick it, whatever omega you want, and then build the circuit, but that doesn't mean you can then use that circuit with a different frequency, right? Because that would change what these two values were. So just, it's fine for one time. But again, we'll see, this is more academic in many ways because, again, typically you're going to be looking at a real circuit and you're going to be defining your values based on an actual resistor or capacitor or inductor, not the other way around. You can't walk in and pull a, can't walk into the lab and pull a negative J2 capacitor off of the shelf, right? So you're going to always know in a real circuit what the capacitance is. However, if you were doing design work, right, and you were working in the frequency domain and you said, oh, I need this, well, that's the value that makes the math work for my function. Okay, you better be careful about what omega it is that you're dealing with then when you go to choose C, right? So you may use it in the design part, but not when you're actually building or prototyping. Okay, so let's go through and solve this one. Since it's already in phasor form, it's a lot quicker. We're just going to define, I'll redraw it quickly just so that I can draw my meshes. Okay. I'm being asked to find I0, right? And so I have 8. And again, now we've been given these, we can assume that they're cosines, but it doesn't really matter. What we do know is that relative to each other, the two different phasors that exist in our circuit do have a 30-degree phase difference, right? So I can go through this. I can apply mesh analysis. So mesh analysis says, assign my little I1. I don't know which order it needs to, I1, I2, and I3, right? And I'm going to apply KVL around each of these loops. Now, I do have a current supply, right? But in fact, the current supplies only cause me an issue, right? I only need super meshes, when I have a current supply shared between two loops, between two meshes, right? But that one is not. So this is actually defining I2. So I2 is not really even a variable. So in fact, let me just, so I don't confuse myself. Right, I'll call this one I2 because it's going to stick around. We'll call this one I3 just for the moment. But what is I3 equal to? Well, I3 is going clockwise, as all meshes should, all mesh currents, right? We try to maintain uniformity going clockwise, but that's the opposite direction of this. So that means I3 equals negative 2 amps with a phase of 0, right? Which we could also write down, if we wanted, as 2 with a phase of 180 degrees, right? It could be, we could write it either way, whichever way we felt made the math easier for us. Those two are equivalent, right? So now when I come to especially this 6 ohm resistor, I can just use this value instead of an I3.
In that case, would the 180 be easier to do the math?
When you're using MATLAB, it's not going to matter, right? It's not going to matter. The only thing is that, again, our convention is that we try to not have negative magnitudes. But as long as you're careful about it, it doesn't matter. It doesn't change the math. It just, if you don't like the negative, use the 180. Okay. Yeah. And again, also, we try to keep phases within, we try to like not go past 360 and things. And so again, it just kind of depends on what you get used to working with. So if this were going to give you a phase of, 390 degrees or something like that, well, then you would either subtract the 360 or you might put the minus, again, it's just preference. It's just preference, really. Yeah. Final result, we should get back to the standard form of no negative magnitudes, and ideally, again, I think the book's not always super clear, but most of the time it's giving you a phase between 0 and 180, and so it'll either do 0 to 180 positive or 0 to 180 negative 180, right? So we'll go through this now and say KCL around I1. Again, it serves as a nice little reminder of our methodology. Again, I start in the lower left-hand corner. I work my way around the loop. So I'm just going to say, 8 I1. I mean, This is, again, mesh currents. They're not real. I mean, I'm using little ones, but they're going to turn out to be phasors. You know, this can't, I don't know. This one's defined as a big one, but it's a branch current, which is, again, usually we use big letters for big I for branch currents and little i's for mesh currents, but big letters for phasor form and little letters for time domain. Whatever, just make sure you realize, right, even though it's a little I, we're doing phasors, right? So 8I1 minus J2, I1, and then minus is just because of the negative that's there, plus J4 times, again, the loop I'm in, I1, minus the loop that's opposing that flow, I2, and I'm back to where I started, so that equals 0. And now I can just clean this up, put it into a standard form, bring all my, collect my like terms, so I have 8 minus J2 plus J4, so that's 8 plus 2, let's see, well, I can combine this, plus J2 times I1, and then my I2 term is just this one, so negative J4 I2 equals 0. And there's my first equation. All right. Now I can, sorry, this is KVL. I wrote down KCL, but it's KVL we just did, right? Voltage drops around the loop. So, next loop, KVL around I2. Right? So again, I start in the lower left-hand corner. I go clockwise around my loop. So I have J4, and this time it's I2, the loop that I'm in, minus I1, the loop that opposes. Plus 6, and again, the loop I'm in, I2, minus the loop that opposes, which would be I3. So it would be negative I3. But I3 is negative 2, so it's, the negatives cancel out, right? So negative, negative, so positive 2. So again, there, yeah, it's easier to not have the 180 in it, right? Because it just cancels out anyways. And then last one, this is just a voltage supply, so plus 10 phase of 30 equals 0. Right? And when we hit voltage supplies, remember that as you're moving clockwise, the sign is the terminal that you hit first. So we're going clockwise around this loop, we hit the positive terminal first, so we write it down as plus 10 phase of 30. Now we can subtract it over to the side where, to the right-hand side of our equation when we go to standard forms. So collecting the I1s together, I just have negative J4 I1, and then my I2s, I have 6 plus J4 times I2, and that equals all of my constants. Well, this 2 from this current supply up here, the 2 multiplies the 6, so that gives me 12, which I'm going to subtract to the other side. So that's negative 12 minus 10. And so here we can remember negative 12 is negative 12, right? It's got a phase of 0. Minus 10 phase 30. So we're going to need to combine those two in MATLAB, right? So you do need to be careful of that. Don't lose the phase. Okay. So now I have my second equation. So 2 equations, 2 unknowns. Again, put them in a matrix form, drop them in MATLAB, solve it. And when you get done, you're looking for I0. So it's going to give you little I1, little I2. Well, how do I find big I0? Well, big I0 is the branch current over here. Well, the only mesh flowing through that is I1. However, it's flowing in the opposite direction. So whatever I get out as I1, I'm just going to put a minus sign in front of that, or a 180-degree phase shift, right? And then that will yield my big I0, which worked out in this case, of course, by our slide, to be 1.194. With a phase of, you'll see here, we've written it as a negative 114. So again, there may have been a minus sign or something, and we end up putting our phase into a format that yields us a number between 0 and 180. negative 114, right, meaning just on the unit circle, we just went this way. Okay, any questions on the mesh analysis? No? It's pretty straightforward again, I think. Very, very similar to everything that you've seen up to this point. Right?